In the first video of this series about the definitions of continuity, we rephrased this definition 2 here into a statement that's concerning distances less than delta and distances less than epsilon, to a new statement that's concerning open balls in the domain of f of radius delta and open balls in the codomain of f of radius epsilon. And this really helped us in video 2 of this series to prove that definition 2, assuming definition 2 to be true, that implies that definition 1 is true. Now, in this video, we're going to complete this equivalence, this proof of equivalence, by showing that definition 1 implies definition 2. Thus, completing the fact that definition 1 and definition 2, these two definitions of continuity, are in fact equivalent. That is, they imply each other. So, let's prove that definition 1 implies definition 2. So, our first step, of course, we're going to assume definition 1 to be true, and assuming that to be true, we're going to show that definition 2 is true. But let's use the rephrasing that we developed, the rephrasing that concerns open balls in the domain and codomain of f. So, instead of trying to show that they're, for all p naught and x, that this is true, let's rephrase it. Let's use our rephrasing. We want to show that if p naught is in the domain of f, so if p naught is an x, then this implies that given any open ball of radius epsilon, given any open ball of radius epsilon, given any open ball of radius epsilon and center f of p naught. So let me just give a quick drawing of this. So here's our x, this is our domain of f, and here's our y, our codomain of f. And so given any open ball of radius epsilon, and center f of p naught, given any open ball of radius epsilon and center p naught, there exists an open ball. There exists an open ball of radius. There exists an open ball. But more precisely, there exists an open ball, that is to say, there exists a radius of an open ball. There exists a radius of an open ball, a radius delta of an open ball, such that if P is in the open ball centered at P naught and radius delta, if P is in this open ball, then that implies that F of P, so if P is in the open ball of center p naught and radius delta, if p is in this open ball, then that means f of p is going to be in the open ball of center f of p naught and radius epsilon. So that's what we're going to try to prove, given that definition 1 is true. So, such that if p is in, I forgot to complete this, given that p is in the open ball of center p naught and radius delta, then that implies that f of p is in the open ball of radius, of center f of p naught and radius epsilon. Now, just a quick aside here, by definition of an open ball, so let me just say, by definition of an open ball, say f of p naught, radius epsilon, this is defined to be all points y in the set y, such that the distance between f of p naught and y is strictly less than epsilon. Sorry, I kind of ran out of room over here. But so we don't have to worry about epsilon being too big. Like, don't get fooled by this diagram. Don't get fooled by, say, like, you might be asking, well, what if I have an epsilon that's so big that I get a point that's outside of y? Well, that doesn't really make sense. This diagram kind of it doesn't make sense for that purpose. The definition of an open ball is defined to be all points y in the set that open ball is embedded in. So in this case, the y. So all points y in the set that the open ball lives in, such that the distance between the center of that open ball and that point y is strictly less than the radius of that open ball, in this case epsilon. So we don't have to worry about this kind of edge case where or we don't have to worry about this edge case that actually doesn't really exist, where the radius epsilon goes beyond the bounds of y, which is something to think about for another video. So let's start our proof here. So let's just take any p naught in x. So let p naught be in x, and let's consider. So now let's consider the open ball of center f of p naught and radius epsilon for any epsilon strictly greater than 0. Well, this open ball, we've talked about in a previous video, open balls are open sets. Let me write that down. Open balls are, in fact, open sets. So, remember, we're assuming definition 1 to be true. So, if we have an open set in y, let's say that this is an open set U, then the inverse image under f of U, whatever that is, all points in the domain of f, whose image under f lies in U. That's the same as that's the definition of the inverse image of a set. So this inverse image, this set, is also open. So we can use that. We can really use that here, and it's very nice, because we have an open ball of radius epsilon for any epsilon centered at p naught, or excuse me, f of p naught for any p naught in x. So we're well on our way to proving our statement. So what can we say about this open ball? Well, it has an inverse image. It has an inverse image under f, the inverse image of this open ball centered at f of p naught, and radius epsilon is open by definition 1. Because remember, we're assuming definition 1 to be true by definition 1. So let's kind of draw out what this looks like. This looks like, well, here's my domain x. Here's my domain x, and here's my domain y. This is y. And let's say here's my open ball center f of p naught, and radius epsilon for some epsilon, or for any epsilon. Here's my open ball, and we don't really know that this inverse image of the open ball is a ball itself. We just know that it's an open set. So we can't really say that it's a ball, but we do know it's an open set because by definition 1. So we know that this inverse image of this open ball of center f of p naught and radius epsilon, this is an open set. And I think it's worth it to write down again what the definition of the inverse image of the open ball centered at f of p naught and radius epsilon, what that really means. Well, it's the set of all points, whose image, so a set of all points in X, the domain of F, whose image under F lies in the open ball centered at F of P naught and radius epsilon. So I'm starting to run out of room here, so I'm going to go to a new page here. So my first claim is the following. I claim that P naught is in the inverse image of the open ball centered at F of P naught and radius epsilon. And it might seem that this is obvious, but it's nice to assure ourselves that this is true. Remember, so we can assure ourselves this is true without a picture for now, that just by the definition, that this open ball, or excuse me, this inverse image of this open ball is defined to be all points, as I said earlier, all points x in the domain of f, x, such that f of x is in the open ball centered at f of p naught and radius epsilon. Well, check this out. F of p naught is the center of this open ball, so it must be in the open ball centered at f of p naught and radius epsilon. F of p naught is the center of this open ball. Let's draw a picture just to reassure ourselves that this is true. Here's our domain x, and here's our codomain y. And this domain x has a p naught somewhere, and then this y here, our codomain y has our open ball centered at f of p naught and radius epsilon for any epsilon strictly greater than 0. And check this out. This open set, the inverse image of of the open ball centered at f of p naught and radius epsilon, p naught must be in that inverse image because it is in fact a point whose image under f is in the open ball centered at f of p naught and radius epsilon. So that's nice to know. We know that p naught P naught is in fact in this inverse image of this open ball centered at f of P naught and radius epsilon. Now, moreover, since we know that the inverse image of this set, the open ball centered at f of P naught and radius epsilon, we know that this inverse image, by definition 1, since the open ball centered at f of P naught and radius epsilon is an open set, open balls are open sets, then therefore this inverse image, by definition 1, this inverse image of this open ball under f is in fact open. Therefore, what can we say? What do we know about open sets? There exists an open ball of some radius, and we'll call that radius a certain radius so that we are almost done with our proof. There exists an open ball centered at f of P naught, and some radius, I'm going to call that radius, and I'll put it in red here, delta. There exists an open ball centered at P naught and some radius delta that is entirely contained in this open set, the inverse image of the open ball centered at f of P naught and epsilon. Let me reiterate something. The inverse image of the open ball centered at f of P naught and radius epsilon. This is in fact a set, and moreover, it's an open set. So therefore, any point in this set, there exists an open ball centered at that point, entirely contained in this set. So therefore, we can say the following: that the open ball centered at P naught and radius delta is contained in this set. So check this out. If X is in this open ball of center P naught and radius delta, or let's call it P, so it's closer to our definition here. If P is in this open ball of center P naught and radius delta, well, that implies that it's also in the inverse image of the open ball centered at f of P naught and radius epsilon. Remember, what did we call this open ball? Remember what we called this? We called this open ball we called this open set the set of all points. The inverse image of the open ball centered at f of P naught and radius epsilon is the set of all points in X whose image under f lies in the open ball centered at f of P naught and radius epsilon. So what can we say? If P is in this open ball centered at P naught and radius delta, and this open ball is entirely contained in the inverse image of the open ball of f of P naught and radius epsilon, then that means that P is in this set. This implies that P is in this set, the inverse image of the open ball centered at f of P naught and radius epsilon. And if P is in this inverse image of this set, then that implies, by definition of an inverse image of a set, that implies that f of P is in the open ball centered at f of P naught and radius epsilon. So look at what we just proved. We essentially just proved it here. But let's just be more careful, and let's just kind of put the nail in the coffin with this proof. So what we just proved here is that given any epsilon strictly greater than 0, that is to say, given any open ball, given any open ball centered at f of P naught, like that is to say, given any radius of any open ball centered at f of P naught for any P naught in X, because the P naught that we chose was just an arbitrary P naught in X, there exists a delta, a radius delta, such that the open ball centered at P naught and radius delta is entirely contained. Well, moreover, such that the open ball of center P naught and radius delta, the image of all the points in this open ball, also lie in the open ball of radius epsilon and center f of P naught. And that is saying the same thing as the definition stated in Epsilon-Delta, in the Epsilon-Delta fashion. We just proved it according to our rephrasing, but we essentially proved the statement because we just showed for any epsilon strictly greater than 0, that is to say, for any radius of an open ball centered at f of P naught, in the codomain of f, so for any radius epsilon centered at f of P naught, of an open ball centered at f of P naught and radius epsilon. So for any, let me say that one more time, for any radius of an open ball centered at f of P naught, that radius, there exists another radius, delta, in the domain of F such that the image of all that points of center P naught and radius delta, the center of the image of all the points in this open ball of center P naught and radius delta those points lie, the image of those points lie in the open ball center, the F of P naught and radius epsilon. So we just proved that definition 1 implies definition 2. And we're done showing that this equivalence is in fact true.